Take it away, Susan.
Oh, thanks for that, Chelsea. Yes, as Chelsea said, this is going to be a pretty introductory session on how to use SPSS for some of your statistical analysis. I've broken it up into kind of two parts. So the first part, I have just a PowerPoint presentation on some basic terminology concepts, and then a look at some different types of statistical tests and what your data would need to look like to perform those analyses. And then the second section, I'm actually going to do some I guess, practical applications within SPSS. So I'm going to bring it up and trying to show you where you would go to perform certain tests and what things you would need to look for. And I have several examples chosen, but we'll time. So as we go along, I'll just check to make sure we have time to get through some of the stuff. So I'll get started. Just bear with me as I share my screen here. Okay. So can everyone see my PowerPoint presentation right now?
Looks good, Susan.
Okay, thank you. All right, so we'll just get right on into it. Sorry, 1 second, I need to move something on my screen. So I guess one of the first things I wanted to talk about was your variables and the measurement scales that they might be on. So the basic ones would be a nominal type variable, or categorical as we like to call it as well, which consists of mutually exclusive and collectively exhaustive categories. So looking at gender and blood type, so a person would only usually belong to one of those categories. Then you have ordinal data, which is basically ordered categories, but there's not really any inherent difference between categories per se. So looking at staging in cancer, you have 1, 2, 3, and 4, or is a patient status unimproved, stable, or improved. Then we get into kind of what we call the continuous type variables. There's the interval, also called numerical, and the ratio. And basically the difference is that within the ratio, there is a true zero. So interval would be something like temperature, and a ratio would be something like weight, height, age, where there is a true zero, and ratios can be measured exactly. I probably just mentioned a couple of these things when I was talking about the different levels, but there are types of variables. So you have the categorical variables, which are the ones I'd mentioned earlier. So they can have could be nominal, dichotomous, or ordinal. And then you have discrete variables, which represent counts. So they can only have a finite number of real values. So the number of objects in a collection, for say. And then you have the continuous variables, which were the ratio and interval, which can be height, weight, blood pressure. And I kind of brought up just a few of these terms to have here because sometimes it kind of gets interchanged, and we might use categorical, we might say discrete, we'll say continuous, but then we might use nominal or dichotomous, which is 2 levels, that type of thing. So I just wanted to kind of bring that to the forefront before we started with any of this. Then there's the, when you're doing your analysis, lots of times you have what's considered a dependent variable, which is your outcome or the response or the effect. It's what you want to find if there's a difference or whatever. And you have your independent, which are predictor or explanatory variables, and they would be the ones that which cause your response variable. So why did I just mention all those things? It's important to know what your data looks like and the type of variables you have in order to determine the appropriate statistical tests that you need. And one of the other things, which I won't touch fully on because this is not meant to be a presentation regarding theory, I guess, around why certain tests are used or stats as such. But I will comment on the fact that there are parametric versus non-parametric tests. And the big difference is that parametric test makes assumptions about your the parameters that you use and from where the sample is drawn. And non-parametric test, there's not as many assumptions that need to be met in order to perform them. Today, I'm mostly going to be looking at parametric tests, but I will take you through a few ways to look at if your data is normally distributed. And I guess a quick thing to look at, there's univariable versus multivariable analysis. In a univariable, it's basically you're looking to specify a relationship between 2 variables. So example, is blood pressure different according to gender? Or do males have higher blood pressure than females, say? And then your multivariable analysis take into account other covariates is able to adjust for these. So the question could then be, is blood pressure different according to gender, adjusting for age and any other weight, height, those type of things, or any other number of covariates. And the most commonly used in the field that I'm been working with within medicine and stuff are logistic regression, linear regression, and Cox regression models for your multivariable. So this is quick. I have a few little tables here to look at what your dependent, independent variable, what the statistical test would be, and basically what it is you're comparing within that. So if we have two categorical variables, say, or maybe you're looking at gender and clinical status in this case, and clinical status is someone's affected or unaffected, and I have males and females. So I'm wondering, is there a relationship between the two variables? In other words, are more males affected than females, say? So that's where chi-square will come in. And the Fisher's exact test is also for a 2x2 chi-square, but it's used when you have an expected cell frequency less than 5. So basically with a chi-square for a 2x2 table, a Fisher's exact will show up in your analysis automatically. And there are some principal assumptions within these things. So you have independent observations. As I just said, your expected cell frequency should be at least 5 for the majority of cells, that type of thing. And then we get into a little bit more, I guess, not complicated, I won't say, but the next level of statistical test. And these are the independent samples t-test, which basically compares the means between two groups. So maybe I want to know the difference in age at death between males and females for some project that you're working on or whatever. So in that situation, your dependent variable is the age, and your independent variable would be gender. And again, there's some assumptions. Your dependent variable needs to be continuous, which is where the interval comes in. Independent observations, having no significant outliers is kind of one of the bigger ones, because if you have it, someone has a off the charts, I guess, result, it may skew your analysis. You want it to be normally distributed, which would be your interval variable. And I'll kind of quickly go through an example of that type of thing once I go into SPSS. But then there's also, if your data doesn't quite meet the assumptions for normality, say, there is the Mann-Whitney U, which compares the medians of two groups, which is used as a non-parametric alternative to t-test. And then there's also the paired samples t-test, which you would use if you had, say, repeated observations on an individual. So maybe your study was, they had a blood pressure taken at baseline, some intervention was performed, and you wanted to know, did it improve the blood pressure? So you're repeating the same measurement at two different time points, and that's when you would use a paired samples t-test. Then this is an extension of that. So the t-test was comparing means between two groups. A one-way ANOVA compares the means of 3 or more groups. So maybe you're looking at mean age at death by cancer staging. So 1, 2, and 3, and 4. You'd want to know, is the mean age different for those who are in stage 1 versus stage 2 versus stage 3 and stage 4, that type of thing. And they have basically the same assumptions as a t-test. And if your data doesn't meet the principal assumptions, and that's where the Kruskal-Wallis would come in, which looks at medians again, which is what's usually used for non-parametric tests instead of comparing means. There's also the one-way repeated measures ANOVA, which is it's an equivalent to the paired samples t-test, I guess, is where you're comparing observations that have been repeated on the same subject. And then there's a factorial ANOVA, which I won't get into too much here, but that's another type of ANOVA. Then we get into, there's correlation. So you may want to understand if there's a linear type relationship between two continuous type variables. So your dependent and your independent are continuous. And it basically, the correlation, Pearson's correlation is used in that situation. And then if your data is not continuous, there's a Kindle's tab and the Spearman. Then you get into what I had mentioned about when you have multivariable analysis, you can get into logistic regression, which in this situation, your dependent variable is dichotomous. So it only has two categories. So whether it's yes or no for death, yes or no for did they have a specific type of cancer, that type of thing. And your independent variables, then you may wonder, well, besides gender affecting having a specific cancer or not, did some dietary thing that you had done, or is your weight or height, or I'm just making up variables here now, but do any of those measures have any impact on that? So basically that's what logistic regression will do. It will allow you to determine predictors to determine if a person has or hasn't cancer. Linear regression it's another way, but in this situation, your dependent variable is continuous. So maybe you're looking at, are there indicators on age at diagnosis for a cancer, say, or something like that. And then the last section, which I may not get into at all with some of these tests today anyway, would be your survival analysis. And that looks at time to an event. And it basically can be, it occurs, or you can use it when you have certain subjects enrolled in a study, and not everybody, and depending on how short or time length your study is, maybe not everyone has the event of interest, but you know that someone didn't have the event of interest up to a certain point, and that's where they would get cut off. So for example, maybe you were looking at time from diagnosis to return of cancer or something like that, and you studied it for 5 years. Maybe not everyone would have had enough time to develop a cancer, but you know that they survived at least 5 years and didn't have redeveloped the cancer. So that would be kind of a situation. So that's where the Kaplan-Meier analysis comes in. And then if you want to look at, I guess, multiple things, so not only did it differ between gender, say, were there other variables that impacted if you had a recurrence or not? And that's where Cox regression would come into play. So I think that's kind of it for that part of it. Sorry if I rushed through, but I wanted to get to the practical part of it as well. So let me just get out of this here now.
Do we want to give folks an opportunity to ask questions?
Sorry about that, Chelsea. Yes, does anyone have any questions now, or?
Not seeing any hands up. So you're probably okay to get going with your SPSS stuff.
Okay. So I apologize here. I have a few notes made for myself because I'm going to try not to miss everything as I'm going through. But I will just start off by saying, I don't know how many of you are actually familiar with using SPSS. I just want to kind of, and I will say this database is just a made up database. It's not relevant to anything, but I guess we could make it assume or whatever that this is just a database that was set up at a cardiac clinic where patients were referred, and we were just looking at age at first clinical presentation. We have some like age at death there. We have were they affected or unaffected based on some X number of clinical factors or DNA, that type of thing. And then we have a clinical marker, which levels 1, 2, and 3, that type of thing. So this is just a fictional database right now, but I will say that usually when you set it up, each row corresponds to a unique individual. And usually you'll have some type of unique ID. And then within that, you'll have whatever information you would fill in for that person would go across the row. I guess one of the things as well, so when you're setting up your data, some of your variables are going to be just a continuous type thing, like you're going to put in age, but some are going to have levels or categories. So if we look at gender, now I know gender right now, just for this purpose, we only have male or female, but we know that could, there are other options. But right now you can see that you would code, in my situation, I have male as 1, 2 as female. And I will say when you're running some analysis, it's important to remember, or I shouldn't say remember, but go back to make sure you understand how you coded it, because it's important when you read output in how you have coded something. So yeah, so another category, like I said, would be the clinical marker. So 1 is level 1, 2 is level 2, 3 is level 3, that type of thing. So go
Susan,
back.
not to interrupt you,
Yep.
I just want to point out that to get to that view, you clicked
Oh
down at
yes,
the bottom and into variable view.
yes, sorry about that. Yeah, so there's two views when you're in SPSS. The data view shows you basically what the spreadsheet looks like full on as, but the variable view, this is where you add in a bit more information. So you can have a label for your variable. You can put in what the values are, that type of thing. Thanks, Chelsea. Sorry, I kind of skipped that little part. Another thing too is when you're setting up the categorical variables, say, if you come back to your screen, normally it's only going to show the 1s and the 2s, whatever your values are. And that's where you would go up to your view tab at the top. And if I click off value labels right now, you're only going to see the numbers. Some people like working that way. I actually prefer being able to see what's actually written there. So that's you tick it on if it's not already showing up in your data set. So I guess I'll just save that now because we're ready to change. I guess basically starting off, one of the things is just to look at descriptives for your study or whatever you may want to go. So you would go to the Analyze tab on top, descriptive statistics, and I'm just going to pick the frequencies tab right now. So maybe I'm just going to look at gender. I'm going to look at the clinical marker, just pick 2 categorical type ones for now. There are options within there. I could pick off the mean, median, mode, the min, max, range, skewness, kurtosis, that type of thing, but that doesn't really tell you much for categorical type variables. But there are a couple little charts that I could pick in here. Now, there isn't a button that you can do more advanced graphing, but just within this statistics, say, I'm just going to pick a pie chart. And for now, I'm going to keep it on frequencies. You could change it to percentages. Each chunk would show that. Just going to go OK. And right now, display frequency tables is ticked off, which is good as well. So I'm just going to go OK. Sorry if sometimes it takes a little while for my actual output to pop up. So here we go. So basically, what that tells us is, in this data set, there's 304 individuals, 179 are male, 125 are female. And we can also look at the clinical marker. There's 3 levels. We have 51, 125, and 128. And then the pie charts, and you can see what it looks like for the gender and for a clinical marker. All right, I'm going to minimize that back down again. So then if we wanted to look, so when I had just said there was other things there, we could do descriptive statistics for, I'm going to reset and maybe choose a continuous type variable. So I'm going to pick age at first clinical presentation, say. So in this situation, maybe we want to know the mean, median, mode, what the min and max value are. I'm going to leave the skewness and kurtosis when I talk about the normality, and maybe percentiles, say, something like that, or quartiles. There, and go continue. And maybe I'll pick a histogram type chart for this. And I'll go continue and go OK. Now, normally I probably would have got rid of at the screen where it says, do you want to display your frequency table or not? Because sometimes if you have a ton of data, that table is going to be massive and you don't necessarily need it. So here we can see the mean age at clinical presentation was 32 and a half. The median was 32. The youngest age was 5 and the oldest was 72. And if we looked at the percentiles, we can see that 25% of people were diagnosed with the first clinical problem below age 24, 25% were diagnosed between 24 and 32, that type of thing. And then if we scroll down to the bottom, it's the histogram chart that we had, which basically shows the age at clinical presentation and how many people had presented with that first time. So if you look at, I don't know, 20 something here, we had about almost close to 30 people that were in that situation. Right? So I'll minimize again. So I guess one of the things when you're running some of these tests is to know if your data is normally distributed or not. And sometimes you want to kind of know that between groups that you're looking at. So maybe you're using gender, you're looking at males and females. So for that situation, you go to Analyze again, Descriptive Statistics, but now I'm going to go to what's called the Explore tab. And within this situation, the dependent variable here is going to be your age at, I'm going to look at age at first clinical presentation, say, and gender. Because maybe I want to do a t-test on this, and I want to make sure that my test or my dependent variable is normally distributed between the for males and for females. So then I know I can use a t-test. So within statistics, I want to, which is clicked off, I'm going to click off the descriptive. So continue. I'm going to go into the plots. I'm going to take off histogram and the normality plots with test. And then I will continue from there as well. I think that's all the things I need to talk about until I actually go into. So I'm just going to go okay. So when you're looking for normality between or within a variable, if your mean, median, and mode are similar, is one of the things you'd want to look for. You also look at what's called a degree of skewness. And basically, if you look at this, we were given skewness and kurtosis values. And here you would take your statistic and divide it by the standard error. And if it falls between, I know this is a bit convoluted, but it's between minus 1.96 and plus 1.96. If you did that division, again, that means it's normally distributed. And I will say that there are a number of assumptions when you want to check this. Not necessarily do all of them have to meet it. And in some cases in real life data, it just won't be able to. It's not set up as a perfect, real world situations aren't a perfect situation. So you're not going to get all of them met. Another thing to look at is your, I'll call it KS and SW statistics. If these, so for male, we look across and the significance is 0.2. and 0.496. So if that's not significant, you can assume it's normally distributed. For the females, you can see that's not the option. It's less than 0.05. So these tests are more, they can be affected more, I guess, by outliers and stuff, which sometimes these may not necessarily meet your criteria, but other parts of your testing does. So if we look at the histogram, and this is where the bell, I don't know how, like I said, how familiar people are with this stuff, but this is where you want your shape to be kind of like a bell curve. So we can superimpose what a normal bell curve would look like by double clicking. Oh, sorry. Double click. Oh, what is it? Double click on your histogram. Sorry about that. And if you go over here, there's a little button that says show, and we want to keep it to see if it's a normal type curve. And as you can see here, the males, as we saw above, the mean and median and mode and stuff, it looks fairly good, and the KS and the WK met it too. If we go down to the female information and we do the same type of thing and we put this one on, you can see that this is probably why some of it didn't meet. Because it's slightly outside, it doesn't fall quite as smoothly, and we had more on the lower end, I guess, of the scale for first clinical presentation. Then a couple other things that you would get in here, I'm going to scoop by that one. There's what's called the normal QQ plot, and usually for normally distributed data, you want the points, the dots to be almost like all on the dark line that you see there, which again for the males looks pretty good. And then if we go to the females, you can see they stray a little bit from the value, from your being normal. And then I'll just go on. The last thing I would mention with looking at normality is the box and whisker plots. And usually with these, for a normal distribution, this line here in the middle is looking at your median. So that would be right in the middle of your box. And these, what you see on the end are called the whiskers. And if they should be pretty equal size to each other. They're the interquartile, or they are the min and max, sorry, of your values. As you can see, the females is slightly off. The line is not quite in the middle. And the whiskers, as we call it, they're higher up there than they are at the bottom. So that was just a quick, very quick session on determining if your data is normal or not. And as I had said, you know, real life situations is probably not going to meet all of the assumptions, but you can just check some of them. And at least this way, you know, if you're using one, the test, it may be slightly biased if you use it based on if your data meets normality or not. So I'm just going to, I guess, stop there. Let's see if anyone has any questions before I go into looking at some specific types of tests. So Chelsea, I don't know if anybody's got a question or.
I had one. I don't quite know how to word it maybe, but so in that case, when we're looking at gender for, what was it, clinical presentation.
Yeah.
So where only the female data was skewed slightly, would you then choose a non-parametric test for the whole statistic?
Well, it depends. Sometimes what people may do as well is run, say, a t-test and then run the equivalent non-parametric test and see if you still get a significant result. Because for the female, some things weren't too off, like your mean and median weren't off of each other very much. And I think when you run the standard, when you calculated the degree of skewness and kurtosis, one measure was off and one wasn't.
Right.
That type of thing. So sometimes people will run a t-test, but if you wanted, you could compare the medians, which is where the non-parametric alternative, and if just to see if it changed your results, I guess.
Oh, and I see a question maybe in the chat here. Christopher says, this is probably outside the scope of this webinar, but is there relatively straightforward way to determine if the sample size is valid from a generalizability standpoint? In other words, if your hypothesis is individuals with children in Ontario make us make use of formal childcare arrangements versus other forms of childcare arrangements.
Sorry, I kind of missed it. What exactly?
So, Chris, I wonder, do you want to just unmute and speak your question?
I'm not sure if it's just that sample size, but that does play a big part in any looking at any kind of statistical analysis, I guess. But yes, what goes into a sample size calculation and stuff is kind of not going to be mentioned here. But one of the things you can look at, I guess, is the confidence interval potentially around your test statistic, that type of thing. You know, to see if your estimate's going to be precise. If the confidence interval is small, you know, you're probably less unlikely that you're missing, I guess, the point. So your alternative hypothesis, if it was significant, you're more than likely it's true for the whole population, I guess. I'm not quite sure if that's what they were referring to, but yeah, this was more of a let's just show how to do things in SPSS and not really the.
Yeah, no, fair enough.
Oh, yeah, Christopher, you became unmuted there. Yeah, I'll just clarify for everyone that you definitely can't unmute yourself, but if you'd like to become unmuted, you can use the chat or raise your hand by clicking the hand icon at the bottom of the screen, and I can unmute you if you like. So, Christopher, do you want to add anything to that?
No. I just wanted to clarify. I kind of expected it wasn't going to be in this seminar, but it's a question I'm dealing with right now and I'm struggling with. So, yeah. Thank you, though.
Yes, no problem. Maybe we can follow up offline if you want to get in touch. I'll put my contact information, and
Sure.
if you'd like some advice, maybe we can provide that offline.
Yeah, thank you.
Does anyone else have any questions before Susan moves on? Oh, I'm not seeing anything, Susan.
Okay, so I guess I'll get into a couple tests that involve just a couple of variables. So like your chi-square, which is looking at two categorical type variables and determining if there's a relationship between the two. And then looking at t-test, determining if within two groups is the mean age. I will go ahead and run a t-test on the age, the variables I'd mentioned, gender, and I think I'm gonna do it for age at death. But I guess one of the things too, before I get into it, is just because you end up with a significant result, a significant p-value, sometimes you also want to know the effect size. So, is it a clinically relevant, is it clinically relevant, I guess, or is the practical significance there? So I'll show you within these what you would want to look for to determine if not only is it statistically significant, but is there practical significance? Because is the strength of the effect that you saw strong? Is it a strong or is it weak or that type of thing? So I'm going to go into analyze descriptive statistics, and we're going to go to crosstabs. So the first thing I'm going to do is a chi-square, and I'm wondering if there's any difference between gender, or is there an association, I guess, a relationship between gender and what I'm going to pick here as our clinical status, say. And in this situation, so gender right now is just coded as male and females, and clinical status is affected or unaffected. So is there a bigger proportion of males affected compared to females, that type of thing? So we're going to go into statistics and chi-square. And this is where the phi and Kramer's V comes into when we talk about the effect size. And is there anything else in that part? No, I think that's all right for there. Then within our cells, I said that weird, but anyway, we're going to, you can have like row percentages, column percentages, total, that type of thing. I'm actually going to just choose row for this right now, and I'll show you what it means to read it when it comes out. And I'm going to go continue, and I'm going to display the bar charts. So I'm going to go okay. So I guess I'm just going to scroll right down to the bar chart. So right now, this is what it looks like. For the males, the blue is the affected, and well, it's almost like a blue, but it's more like a teal, is the number of unaffected. So you would think just by eyeballing, it would look like that more males. Now we just want to know if that difference is statistically significant. So this is where we go back up to our table, and I have it set up so it's a row percentage. So if I look across from males, I have 132 affected, 47 unaffected. So that means 73% versus 26. And if you look at females, it's 61 versus 39% are affected versus unaffected. So we go down to our chi-square table. And across from the Pearson chi-square, it is showing to be statistically significant. It's less than 0.05. And this is where I had mentioned on the in the PowerPoint, there is a Fisher's exact test. So if you look under here, this line would say however many cells have an expected count less than 5. In our situation, that didn't occur, so we don't necessarily have to report the Fisher's. It would be the Pearson chi-square is fine. And if you look here, this is kind of your the phi and the Kramer's V is basically the looks at the strength of the association. So there is an association that's statistically significant, but it's not super strong. There are some standards they use for what's considered to be significant or not significant for these values. Even though this shows it as being significant, the effect is fairly small. It's not necessarily clinically or practically significant, I guess would be a way to put it. But anything under 0.1 would be considered a small effect, 0.1 to 0.3. So we would fall in that. There is a moderate effect. And then I think above 0.5 for this value is considered to be a strong association. Now I just did this for a 2x2. But for the sake of time, this could have been done for a 2x3, a 3x3, could be done for any size table. So basically, if you were to report this, I guess if you were doing the study, you'd probably, you could report some of the percentages if you wanted to. You would report the chi-square value to be 5.7, and you'd put in your p-value would be 0.017. And you could also then mention the effect size as well, either report your phi or your Kramer's phi. So I'm going to go on now to the, unless anyone has a question.
I don't see any hands up and nothing in the chat.
Okay. So, just thumbs up. Okay, so I'm going to go on to a t-test now. And for this one, I'm going to look at, is there a difference in mean age at death, say, based on gender? So I'm going to go down. For this one, we want to go to what compare means. And this is an independent samples t-test. And there's the paired samples I'd mentioned and your ANOVA, which we will get into after. So I'm going to go to independent samples t-test. So for this one, the grouping variable again is going to be gender. And the test variable is going to be age at death. So I'm going to go bring that over. As I go into, so when you're doing the grouping variable, it wants you to define the groups that are in there. So maybe gender had more than 4 categories, but I was only looking at more than 2 categories, sorry, but I was only looking at males and females, or whatever your grouping variable might be, because within t-test, you're only looking at 2 groups. You have to go in and specify. So in my situation, males were 1, 2s are females, but maybe we were looking at cancer staging and we only wanted to look at 2 and 3. In that situation, you'd have 2 and you'd put in 3. It all depended on how your data is coded and what groups you wanted to look at. So I'm going to go continue. And I'm going to go, okay. So let me just scroll this over a bit. So from the t-test, so we can look, and we had, there was 101 or 111, sorry, but you can see that we only had age at death. So for females, we only had 20, but we had 91. The mean age is 39.5 and 56 or 57 for females. One of the things you also look for outside of normality is looking at equal variances. And you can get that from your independent samples t-test table. You don't have to do any other analysis. It's this Levine's test statistic. And you go across from, you want equal variances assumed. If this is non-significant, it means you can use this line of data. So basically, we're going to scroll across. We can see the mean difference was 17 years between age at death in males and females. And you can see your confidence interval. And you can see here for the 2 static significance, it was 0.001. So it's less than 0.05. So we can make the statement that according to what we've looked at right here, there is a significant difference in death between males and females within this group that had presented to the cardiology clinic. And this is your effect size again, looking at the size of it, I guess. And, Cohen's d is one of the ones that's usually used within a t-test. And in this situation, it's usually, if this is the estimate you're looking at, and I think for this one, if it's 0.2, it's considered small. If it is 0.5, it's considered medium, and anything above 0.8 is considered large. So in this situation, we're saying that there is a strong effect size between age at death between males and females. So within this, when you were going to report it, I guess you report what the mean ages were for both groups. You would present what your T statistic is, this here, your 2 static significance, and also report information on your Cohen's d for this one. Probably is one. There are many different ones, I guess, but some are some of the usual ones to be used, I guess, would be The phi and Kramer's V that I mentioned, chi-square, and then for t-test, it's Cohen's D. So I think that's all I'm going to say about the t-test. If anyone has any questions, you can ask them before we move on to the ANOVA, which is just an extension that includes more than 2 groups. Okay, I'm just going to move on. So for this situation, maybe we want to, within this database, there was a variable called clinical marker, and you could have one of 3 values. You could have a level 1, you could have a level 2, or you could have a level 3. And our question was, we were wondering if there's a difference in age at death between if you had one level 1, level 2, or level 3. So in this situation, you're going to go into your one-way ANOVA. And again, your dependent is continuous type variable, and that's your age at death. And again, this could be any kind of continuous variable that you're looking at. It could be maybe you're looking at height or weight, and you're wondering if there's a difference between certain groups, or maybe blood pressure between certain categories of a categorical variable, that type of thing. I'm just using age at death because that's one of the ones I have here. And I'm looking at this now between the clinical marker, which is our factor. And one of the things, once you get past the 2x2 test, you want to know, so not only is, if it does come back significant, say, is there a significant difference between level 1 and 2, level 1 and 3, or level 2 and 3, say, when I'm looking at 3 levels? So you want to know within that breakdown, is there only specific categories that are significantly different from each other, or are all of them? So that's where the post-hoc tests come in. Some of the usual ones to use, I guess, will be Banferroni and Tukey's. I'm going to take off for my situation here. And I'm going to go continue. Under options, I'm going to get some descriptive statistics. And I'm going to do the homogeneity variance test, which is the Levene's, the same as what was mentioned for the t-test. I'm going to go continue and estimate effect size for overall tests. I'm going to tick that off. So I think for this, it comes out to be the eta squared for ANOVA. So we'd already typed the Cohen's D and the phi and Kramer's, and now this will be another situation. So I'm going to go okay. And here we have the tables now. So under our descriptives, we have 3 levels. We have the means. So for level 1, the mean age at death was 38. The mean age for level 2 was 43. And the mean age for level 3 is 48. So there are differences there. So this is the homogeneity of variance test to Levene's again. So we're looking at means right now. And if we scroll across, it is just above the 0.05. So we are going to assume that we met that assumption of equal variances. We're going to the ANOVA table now, which gives us an overall significance of, is there a difference between levels of our categorical variable? And if we go across, this is F statistic and the associated significance, and it's 0.015. So we're going to say it's less than 0.05. So there is a significant difference. But how strong is that difference? And that's where the effect size and eta squared comes in. And for this one, anything less than 0.01 is a small effect, 0.06 is a medium effect, and 0.14 is a large. So we're just above, say, a medium strength for the difference. And now this is where I'd mentioned within categories. So this is where the post-hoc test comes in, and I'm just going to use the Tukey's part of this table. So we have level 1 versus level 2. And if we scroll across, we find a significance of 0.220, which is above 0.05. So there's actually not a significant difference in mean age at death between level 1 and level 2. However, if we compare level 1 and level 3, there is a significant difference. And then this will give you this will be the same thing. So if we look at level 2 and level 1 here is the same as level 1 versus level 2. But this also shows us, is there a difference between level 2 and level 3? And the significance for that is no. So the only groupings where there is a significant difference, even though the overall model is significant, it's basically between level 1 and level 3. So if you, once you go time to report your results, basically you could report what the means for each of the categories are. You would give your F statistic and the overall significance for the analysis. You can give your effect size, but you would also probably want to include within there that these levels for the post-hoc tests. Because even though overall model, we can't say it's not significant between all levels. You would put in that level 1 versus level 3 is where the significant difference existed. So I think that's it for the one-way ANOVA. So I'll stop again now if anybody has, I know I'm going through this fairly quickly. It's a lot of information to try to squeeze into, I guess, one webinar. Is anybody have any questions right now, Chelsea? Is there anything showing up?
I don't see anything. As an observation, I guess I'm making is that it seems like for the tests to determine if you've met your assumptions, you would want it to be non-significant, and for the rest of it, you know what I mean? That seems to be a pattern.
It all depends on what it is you're looking at. Like the homogeneity of variance test, the Levine statistic, you want that to be non-significant.
Right.
But when you're looking at your effect size and stuff, that's based on some, I guess, general cutoffs for what's considered small, medium, or large. And this differs for every, what's the right word here, for every different effect size. So like I'd said, for chi-square, you would look at phi and Kramer's V, and there's different values that will be considered small, medium, or large effect. For Cohen's D, or for t-test, it's Cohen's D, and there's different values that is considered a small, medium, and large effect. These things can all be kind of found on, if you want to Google them, because there's different things. So it's not necessarily showing a significance value, it's a point estimate. But yes, they will show a significance thing. And then for this one, say for postdoc, you want certain things to show which is significant or non-significant.
Right.
Yeah. It all depends on what it is. Some things you want to so for the for equal variance is assumed, again, this is another thing you're looking at. That's the Levine's again. Sorry, that's, you want that to be non-significant, whether it's in a t-test or whether it's in, there's different theory behind all of this is a little bit outside of this presentation, but there are rules of thumb on what to look for when you are running a test and where you would find them within the output that's given from SPSS, I guess.
Yeah, that's really helpful, Susan. I'm not seeing any other hands up. We've got about 10 more minutes, so you've got some time.
Okay, so I'll move on to a regression type analysis now. So for this one, I'm going to choose the binary logistic, and where the question is basically, is there a difference in those who died or didn't die? Or what was death affected by, I should say, gender. So we know there's 2 categories for that variable. Based on the clinical marker they were found to have, which has 3 levels, 1, 2, or 3, or when they were diagnosed with their age of first clinical problem. And again, this is not a real world example by any means. This is just set up to kind of provide some output and how to read SPSS printout. So for that type, and again, I'm using death, but this could be used for any type of outcome variable that has 2, or dependent variable that has 2 levels associated with it. I'm just using death, yes or no. So for this one, we want to go down to regression and binary logistic. And I will say, before I go too much further, there are a lot of tests that can be run in SPSS. A lot that I've never ever used. Some are used fairly frequently, but it all depends on what kind of, I guess, study design you have, what your study is. I was involved in a few genetics research studies and some other, I guess, health related ones. And back then when we were running them, a lot of the analysis was time to event. so survival analysis. So I was more familiar, or logistic regression, say, because in those situations, you want to know more than a relationship between two variables. Say you want to know if there's more than, maybe there's more than one thing that impacts, and this way you can adjust or adjust for all of these variables and still determine if there is a significant impact of one variable while controlling for the others. So as I said, for this one, our dependent variable is going to be, did they die or not? And then the factors, or the covariates or independent variables, I'm going to use gender, the clinical marker. And I'm also going to choose a continuous type variable, which is going to be this age at first clinical presentation, say. Now, one of the things when you set up some of in the logistic regression, and it's similar for Kaplan-Meier and Cox regression type thing, for your categorical variables, so this is where, when I had mentioned in the beginning, it's important to understand how your variables are coded. Sorry, one second. So for gender, any categorical variables, you want to bring them over and you want to determine a reference category. So for gender, for me, I want to compare males and females, but I have it's coded as 1 is male and 2 is females. So in my situation, I wanted the reference to be females, which is 2, which is the higher of the categories. So I'm going to choose last. And I know that might have been confusing, but I'll try to explain it again. So for the next one, say clinical marker, that has 3 levels, which is 1, 2, and 3, how it's coded. And maybe I wanted to compare the other issue, or the problem, I guess, is the more categories you have, you can only have the reference category be the first or the last one. That's kind of the limitation with doing it this way. So I want to consider in my situation that level 3 is going to be my reference. So I want to compare level 1 to level 3 and level 2 to level 3. I can't compare level 1 to level 2 this way. I'd have to set it up as first, level 2 versus level 1, and versus level 3 versus level 1. But then level 2 and 3 don't get compared. So you have to kind of remember these things, but I'm going to have my gender as being males to females, and females to males 1, so it's last. And I'm also going to choose for the clinical marker, I want level 3 to be my reference category, and that's going to be the last. Age at first clinical problem stays there. That's not a categorical variable. So then under the options, I'm going to take off the confidence interval and exponent B, and I'm going to take off the goodness of fit. So how well your model is actually predicting death or not. So I'm going to go continue. I think that's all the things I need to tick off here right now. So let's just go into the model. So I'm going to scroll up here. Okay. So we did have 304 people in this data set, as we knew from some of but not all of the variables had information. So age at first clinical presentation was not there for everyone. Maybe there had been a missing gender, or maybe there was no level. So when you run a lot of these analyses, you're only going to get people that have information for all of the variables included. So that's why we're down to 163 people right now, because there's missing information. And hopefully when you set up your data set, you don't have as much missing data as what this one has. But it was something I wanted to highlight. And it is going to happen. You are going to have missing cases. So one of the things to look at when you're doing logistic regression, I guess, is to make sure you understand how your dependent variable is coded. So my dependent variable, remember, was death. 1 is yes, and 0 was no, sorry. And usually when you read any of these, so it's basically saying dead to not dead. So whatever our way we want to word this, we're looking at basically its impact on death, because we're looking at 1 to 0, which is dead to not dead. So that's going to come in down here when we try to read this categorical variables table. So here, remember we had chosen level 3 as being our reference, which is why there's just zeros. when we go down to the variables in the equation table, you're going to see a level 1 with a 1 by it. That's going to mean it's comparing level 1 to level 3. When we get down and we see this one and it has a 2 by it, it means we're comparing level 2 to level 3. And we're comparing males to females. And then we're going to go scroll down past this here now, and we're going to go down to. So one of the things I guess I would look at first is this Cox and Snell, and I don't know how to pronounce this one, Nagelkirky or whatever. Basically what it is, it explains, if the model explains the variance in death or who dies and doesn't. And the models explain about 34 to 47% of the variance in death. This Hosmer and Lemishow test is basically a statistical test for, is it a goodness of fit for the model that, or for the information we have, did the model fit it? And you want a non-significant test. So again, Chelsea, this is one of those situations where you want a non-significant value. So we're saying that, you know, we use, it fits the regression model fairly well. And then we scroll down to look at our classification table that pops out, and it shows what our observed versus predicted would be. And this number down here, overall percentage, basically tells you that the model we chose correctly classified 77.3% of cases. So based on what we had, it was, you know, it correctly classified at 77% of cases as being dead or not dead. So this is the beef of the, I guess, the table. And in logistic regression, this exponent b is considered to be an odds ratio. So if we look at gender, for instance, and remember we are comparing males to females, and it is looking at who died. If we come across the table, we have a significant result. Exponent b is 7.22. And what you would report would be that the odds of dying is 7.2 times greater for males compared to females, because that's the way we had it set up. It's males to females. This is, and then we look at the clinical marker. So remember, this is level 2 versus, level 1 versus level 3. It doesn't quite reach significance. It's just above 0.05. But if that had been below, it would mean that those in level 1 were the odds of dying was 3.6 times higher in those with level 1 compared to level 3. But there was no difference in the odds of dying for level 2 and 3. And then I guess the last thing would be the continuous variable, the age at first clinical presentation. And again, that came back as being significant. So the way this would be kind of read is that for every, because it's above 1, for every year as you go up in age at clinical presentation, your the odds of death increases by 6.3%. So the older you were getting diagnosed, it increases your likelihood of dying. And I know it doesn't make intuitive sense, and it's just the way it's set up, but maybe it was by the time they were diagnosed, there was no treatment. If you got diagnosed young enough, there was a treatment, maybe they survived longer, is a potential reasoning for why that could happen. But I guess that's basically it, because I just realized it's after 1 o'clock.
Yeah, we're a couple minutes over here. So thank you. Thank you all for staying on. Does anyone have any questions for Susan? I'm going to put a couple of addresses in the chat here and my email address. So I just want to say thank you to everyone for joining us today, and thank you very much to Susan. That was a really great refresher on how to use SPSS and some quantitative analysis. I know I'm going to be revisiting this when I start to analyze some stuff I've got on my desk. So I will say that the presentation will be available on our website in the coming weeks for those of you who also want to review it and to go back to those great tables that Susan shared at the beginning. And I just want to let you know quickly that a few feedback questions are going to pop up on your screen when you leave the webinar. So if you have a minute, please answer the questions so that we can improve our free trading program. And don't hesitate to reach out. As I said, my email address is there in the chat. You can also follow us on Facebook or visit our website to stay up to date on upcoming sessions. On March 15th, we have another session in this series where Dr. Holly Etchegary will be running a workshop on refining your research question. And our research program, Quality of Care, is hosting the third webinar in their Healthy Discussions series on March 28th, and that'll be a discussion about the impacts of oral health on overall health. And registration for that session, again, is at the link, the Quality of Care link there in the chat, and will be available next week. So again, sorry that we're 4 minutes over, but thank you all for joining us today, and I hope you have a wonderful weekend.
Thank you, everyone. Sorry for running over.
No worries. Syed, yes, I can send you a recording of the session when it's available. Excellent. Bye.